Thank you for a kind introduction. It's a great honor to be here. Let me, relax you a little bit after this deep result in number theory about my name. During the war, my parents decided that it's best for my mother to take all the children away from Taipei, moved to a small village, and became a farmer. I was born right after the war, and the neighbor found out that my mother was not in the field since early morning, so they went to check, and there was a baby. And my mother was so happy, said, we don't worry about fortune teller, no other consideration. The name of my son is Peace. Okay, and that's Tai-Ping. My mother does not read or write, but with multiplication table, he could do wonderful calculation. So I went to market with her to sell some vegetables, some chicken, and so on. Then my mother went around to help other farm lady. She just feel that she should not leave all the calculations to the city folks. So she was there to help the farm ladies. And so she told them that actually it's very easy. For the price of the geese today, you accept certain basic point, like 3 ounce, 6 ounce, 9 ounce, and then for the actual weight of your geese, you do some simple interpolation. It's not easy to have this period of joy in doing mathematics in this chaotic world. To spread this rational thinking is really our duty. Okay, so I want to talk about the kinetic theory and the fluid dynamic. First, I started with the gas dynamic. Then I moved to kinetic theory, and then stay there. And now try to move back, and which will be somewhat different fluid dynamic, which some people may call it modern fluid dynamics. So what is fluid dynamics? Well, you have, say, gas in this room, and you have a typhoon, and you have a pressure, which is high pressure here, low pressure, it moves, and there's convection, and so that's fluid dynamic. It involves macroscopic velocity, a variable. But there's another way started by Boltzmann. He said, actually, we could also view the gas as a bunch of particles, and the particle follow Newtonian law. So here's the picture there. You have this distribution function. So when we say that this point has a temperature, we don't really mean this point. We mean a small area there. Temperature is the averaging of the motion in this small volume. And so this is how one connect the kinetic theory to fluid dynamics. You average, you integrate. So let me start two equations. The first one is order equation, which is called very old equation and most basic one. And it has no internal energy, no internal structure, no memory. And then there's a Boltzmann equation for the kinetic theory. I don't want to bore you with this equation. Suffice to say that they are not easy to solve. Okay, but the order equation, although it's the simplest one, but it has captured some of the very essential things, namely nonlinearity. So this is one of the things that for non-physical sciences people here, one of the important things is to have the right formulation. So the order equation, which I write one dimension, has 3 equations, and you write it in vector form, such ut plus fux equals 0. If you do that, then immediately you say, well, we need to find f prime u, which is the metric. I need to find eigenvalue, and which allow you to compute the speed of sound, for example. Now, this is very nonlinear, because the speed of sound lambda u depends on u. So of course we know the speed of sound is 300 some meter per second, but this is in this room. If you are in an airplane up there, the speed of sound is much slower, and it depends on the state of the air, the temperature, and the density. And this is very serious, because the sound wave could collide each other, some faster, some smaller. And this gives rise to something called a shock wave, which is simply a wave which is discontinuous. Of course, we have experienced this. Sometimes suddenly become hotter, suddenly become colder. And in the order equation, is idealized, is a discontinuity. Now, the PDE has a derivative. We all know in calculus, you cannot take derivative of a discontinuous function. Well, but the physicist has a way to say that, well, before we have PDE, actually come from the integral equation. And mathematicians say, okay, we have a series distribution. We talk about weak solution. But in any case, you come down to a jump condition, which is this one here. And this is a constraint. So my first result in around 1973 in my dissertation is to say that we need a entropy condition or admissibility condition. So and the U minus here, U plus A, which is discontinuous on both sides, it needs to be on certain curve. And my condition simply says that the speed has to be minimum there. Never mind this, I just find out that life is okay. But after many years, with Tommaso Ruggeri, we give it a more direct physical meaning, which says that actually wave like that is if and only if this wave can be realized by increasing the entropy production. Entropy is a physical entropy. And there's a lot of theory, a lot of history behind that. Let me just say Hans Bethe. Hans Bethe is the person who do all the important calculation in the Manhattan Project. And he, of course, is a great physicist. He looked at this thing when the speed is monotone. And there are other great mathematicians like Peter Last, Olga Olinik, Hermann Weyl did it independent of Hans Bethe, because Hans Bethe work was classified that time. All right, so the question is, now that we have this shock wave, we have admissibility condition, so the mathematician asks, can we have a theory out of this? Okay, and this is the first step is to something called a Riemann problem. Started with Riemann, and then there's actually we have a theory. And that was done by starting with the great paper of James Glynn, 1965, and he occupied a good part of second half of the 20th century. And this paper by the Italian Bianchini-Bressan has a vanishing viscosity. Okay, so this is the order equation, the fluid dynamic part of my talk. But I want to say that order equation, which is really very simple, it connotes a lot of things, but it can effectively describe a physical phenomenon in a large scale. So if you have an airplane which is moving this way, then there's a shock wave, because air, you move, air is compressed, form a shock wave. And then there's a shock wave behind it, and so it's an end wave. And this one can describe by the order equation. Now, every field has a success. And then there's a time when we don't know what to do. And I say that, like a Riemann problem, there are self-similar solution. This is just simply to say that this should be the beginning of an exciting time for multidimensional phenomenon in shockwave. Okay, so let me say that I want to go to Boltzmann equation, but I need a bridge. And the bridge is never saw equation and some relaxation model that occupied me the time when I was a colleague of Professor Dang Zagier at Maryland. Now here's the Boltzmann equation. Now the Boltzmann equation, even writing down the equation is not easy. But anyway, you guys move around. How does it change? It changes due to collision. Okay. All right. And there's a conservation law which was found by Maxwell. But Boltzmann believed in atom, and so he derived it from his Boltzmann equation. The thing that's really important for the Boltzmann's thing is that he realized that if I multiply equation by log, and then wonderful things happen. You have an inequality, which means that the process is irreversible. Now, this is a very big historical, philosophical, I should say psychological thing, because he started with a Newtonian thing. And now you have an inequality, something irreversible, which is like a thermodynamic. So you start with Newtonian, which is reversible. You end and have a bridge here, the Boltzmann equation. You end with irreversible H0. Now, these days, when you talk about AI, they talk about Boltzmann equation. Although it's not this Boltzmann equation, but it's really originated from this H0. Okay, so H theorem says that the gas can be any state, but eventually it goes to this finite dimension manifold, which is thermal equilibrium. And this is what H theorem says. And it's around this thermal equilibrium that the fluid dynamics phenomena occur. So you have this mean free path, which says that if the gas bump each other very frequently, and then in the limit, you got the order equation. So that's this Hilbert's sixth problem. He said, well, okay, let's start with Newton and end up with the Navier-Stokes order, the fluid dynamic. How does this go? And how about the idea of Boltzmann? So this is one part, important part of Hilbert's sixth problem. Now, Harold Grad of NYU in 1963 said, okay, Boltzmann and fluid dynamics, they are related, rather reasonable, and Hilbert, the great mathematician, actually initiated such a thinking. However, there are places, very crucial places, called singular layer, which need to be studied in order to bridge these very two distinct descriptions of the fluid of the gas motion. And okay, so you have this singular layer. So in this room, basically, is equilibrium. But if there's a temperature sudden drop near the wall, this is a very drastic change, and that's a singular layer. And you need to study this to connect to the room inside. So with Sixian Yu, starting this century, we focus on this topic. And, mathematicians do mathematics has several different ways. One way is to do it very concretely. And in order to do that, you have to have a strong quantitative method. So this picture is a cartoon picture, meaning that if we have this room, which is the equilibrium, you can apply thermodynamics. Then you have a bunch of particles, and just push to this side and see what happens. Well, you begin to talk to the ambient air and become to give rise to sound wave, thermal wave. On the other hand, it maintains the particle identity and still get together but decay exponentially. So this is something very concretely constructed. People who in the field will know that Boltzmann equation is one equation. But if you compare the fluid dynamics to use a PD, actually it's an infinite number of PD. So to construct these things, use a mathematical analysis, it does not work. And let me just simply say that this take a very different thing to work. Okay, thank you. Okay, so we then tried out this green function approach for the quantitative description of the wave. So here is the boundary, free zone, the wall, see. And then you have a very interesting boundary layer, and then the fluid layer, and this coupling of this. And then we look at the collection of trajectories, and you have an interesting bifurcation phenomena. This is something that the Kyoto School under Yoshio Sone has spent a lot of effort on this. And Shixian and I has a mathematical analysis of it. So the challenge in the field is that, suppose I start with kinetic theory, go back to fluid dynamic, then you need to study all this coupling of the singular layer, which separate the fluid dynamic region from really truly kinetic region, and which occur on the boundary, near the shock, and the initial layer. But more generally, the fluid dynamic phenomena, there's an experiment, important experiment called radiometer, and which cannot be explained by classic fluid dynamics. So this is a things which is need to be carried out from kinetic theory. But more generally, suppose you have other field, and you would like to have a phenomenological law, say in biology and so on, but you need to go inside that layer and to study what actually going on there. And we provide an example where we have a strong quantitative method started with the green function to study what happened inside the layer. So this is an example, and one can think of that when one have other phenomena. Okay, so thank you very much.
Thank you, Professor Liu. And are there any questions to?
It's not a question just for fun. As well as our having been colleagues for 10 years, in your talk, Green's functions played a very big role.
Yes.
In the formula with Gross that I mentioned, I didn't say it, but the key role is played by Green's functions.
Okay.
Yeah, so this is the unity of mathematics.
All right. So there's certain universality there.